Hello everyone, it is my pleasure to introduce our work, Cross-Modality 3D Object Detection. Camera and lidar are two complementary sensors for 3D object detection in the autonomous driving context. Cameras provide rich texture and color cues while lidar specializes in relative distance sensing. Camera is good at understanding the world while lidar is good at measuring the world. The challenge of 3D object detection lies in effectively fusing 2D camera images with 3D lidar points. Although images and point clouds are two different modes in form. But in essence, they both represent the world. If the sensor is calibrated when the data is collected, and the collection time is synchronized, then the collected image and lidar point cloud should meet the geometric constraints. Specifically, lidar points correspond to unique pixel points on the image, and the lidar point cloud should be located in the 3D frustum space obtained by image projection. Inspired by point RCNN, we segment the raw point cloud based on the point-wise fused features, and generate 3D proposals from the segmented foreground points simultaneously to constrain the search space for 3D proposal generation. These 3D anchors are located at the center of each foreground point, and then projected to images for 2D anchors producing. Benefited from the projection, there is no need to seed extra 2D anchors of different ratios for images, because its scale-adapted benefited from projection. With the anchor generation mechanism, 2D and 3D regions are tightly connected for following classification and regression. Since images have important semantic information for 2D detection, and point clouds can provide essential geometric structure information for 3D target detection, we choose to let them do what they are good at. Specifically, the 2D anchor is used for 2D regression and classification, and the 3D anchor is used for 3D regression and classification. After the respective training process is over, the 3D proposals will be projected to the image plane, and then calculate the reprojection loss with the 2D proposals. Since the 2D and 3D anchor pairs are naturally produced by our joint anchoring mechanism, they can share information during training from each other. As shown in the figure, we use two-stage feature fusion to explore the interconnection between these two modalities. During first stage, the upper part is a modified ResNet 50 and FPN feature extractor, and the lower part is the 4-set abstraction module and feature propagation module of PointNet++. Image feature maps of different scales contain different levels of semantic information and receptive fields. Similarly, set abstraction module is designed to build a hierarchical grouping of points and abstract larger and larger local regions along the hierarchy. So we propose to apply point-wise fusion at different levels of feature maps, to enable points to possess high-level semantic information from RGB images. Although we have conducted point-wise fusion to enrich points with high-level semantic information, it's only point-to-pixel level fusion, which may be still too sparse for learning specific local features of each proposal. So we propose to apply ROI-wise feature fusion to learn denser representation for refinement, which is a region-to-region level as depicted. This is the architecture of our proposed network. It consists of two stages, region proposal stage and box refinement stage. The first stage aims at generating accurate proposals by applying point-wise feature fusion and 2D-3D coupling anchors. The second stage conducts ROI-wise feature fusion to learn more robust representations, and predict final confidence in box refinement. This is the performance comparison of 3D object detection with previous methods on the KITTI test split by submitting the results to the official test server. The evaluation metric is average precision with IOU threshold 0.7 for cars. To further analyze the ability of our proposed deeply fused multimodal 3D object detection method, we conduct extensive ablation studies on the KITTI train and validation set to explore the effects of our components. We use the official training and validation split and accumulate the evaluation results over the whole training set. The effects of each component are shown in the table. We show qualitative 3D object detection results of the proposed detector on the KITTI benchmark in this video. We can observe that the predicted 3D bounding boxes fit tightly to each object, even for the distant and highly occluded cars.